So, introduction to the delta Y transformer connection, part 1. This is the first part of the series for delta Y connection. So let's just proceed to draw the single phase transformer with two windings. And this left side you will assume the primary high voltage or the source, and the right side is the secondary or low voltage or load. So next we will draw the polarity mark to indicate priority side of the winding, and also draw a parallel to indicate magnetic coupling. So we will assume that the primary voltage is 4160 and the secondary is 480 volts. So ang primary natin capital A and the secondary is small a. So natin single phase. So para may isang 3 phase mag-add tag 2 ka windings, so A, B, and C. So natin transportation. So we can start to connect the secondary windings. So first connect the A to B and B to C together, and also they have neutral wires. So mato natin wire grounded the transformer connection. So ang Y grounded transformer connection is na different characteristic hasta ang Y grounded transformer connection. So i-connect primary delta. Many ways to connect delta, and each connection give us unique characteristic. Explore lettering modules, but one of the most commonly delta connection is the AB or DY1 connection. So let's connect delta connection like such. So mana delta Y grounded 3-phase transformer connection. Introduction delta Y transformer connection part 2. Also part 1 we tackle illustrated very commonly delta Y transparent cause. Part 2 we discuss learn shape line to line and phase voltage for adult and Y connection. We understand that phase voltage is measured across transforming windings, so I'll let you know straight primary phase voltage across measured polarity and non-polarity. So ato siya kapihon primary base voltage, primary B, and primary phase voltage. The secondary side will illustrate secondary phase A voltage, secondary phase B, secondary C phase voltage. So line to line voltage, however, are measured across two lines. The most two lines measured across the line A and line B, from line B to line C, and from line C to line A. So on the primary side, where our transform is connected to the delta, we should expect the line to line voltage across line A and line B to equal phase A voltage. Now it's very important to visual verify this is a relationship to get a initiative understand. Supposed to be label point A and point B. So measurable point A is the same point on the line as the polarity side of the winding if the point B is the same point on the line as on the line polarity side winding B. So if we measured approach point A and point B, we actually measured across the polarity side of winding A and non-polarity side of winding A, which we are defined as our phase voltage. Similarly, the line to line voltage across line B and line C is equal to phase B voltage, and the line to line voltage across line C and line A is equal to phase C voltage. So for connected transformer, we should expect voltage across two lines to equal the voltage across single winding, or in other words, line to line voltage is equal The phase voltage, the most common line measure of the A in line B across the line B, line C, dash line and line C, line B and line A. The line-to-line nodes measured across line A is equal, piece is B. For a while connected transformer to negative especially to line voltage is equal to square root of 3 times voltage. These are certainly going to shift to voltage. So to pull the phase angle of the second degree voltage and phase voltage, what the line to line between the line B and line C. That's it. The base B and what is minus LC, which is equal to square root of 3, the magnitude of base voltage, which is also equal the square root of 3 times the magnitude of the PC voltage, or simplify root of 3 times magnitude of any phase voltage, assuming that the balance set of voltage between line to line voltage and phase voltage. Looking actual number, if you took a super duper ultimate measured across line A and B, the primary side transmission expecting 460, it's aligned to information shown that the part 1. Now since the primary side of the transformer is connected in delta, we should expect the line to line voltage to equal our phase voltage. Somehow get the transformer a measure different in potential between the polarity side avoiding a non-polarity side avoiding. We should expect the voltage of the 4160 similarity in the line-to-line voltage across line B and line A should equal 4160, and the line-to-line voltage across C and the line should be equal to 4160. Both phase B and phase A voltage should also equal 4160 over delta connection transform lane is equal to phase voltage. Only in the secondary arms are connected in Y. If you measure the cross line A and line B, we should expect 480 voltage for line-to-line voltage. Again, voltage that we define a part 1. So what voltage should we expect the measure across the polarity side in winding a non-polarity side of winding a? Well, should be derived and from line to line. Remember that the relationship for a Y-connected transformer aligned to line voltage across the line A and line B is equal to phase voltage minus B voltage is equal to square root of 3 times any voltage. Since already know that the line-to-line voltage is 480 voltage, we simplify all the phase voltage by divide 480 voltage by square root of 3, which given approximately 277 voltage. So phase of voltage is equal to 277 voltage. Then the rate of phase B voltage equal to 277 voltage, and VC voltage is also equal to 277 voltage. And the line to line across the line B and line C is equal to 480 voltage, and line to line voltage across line C and line A is equal to 480 voltage. In this part, we look at the line to line voltage phase relationship with delta Y transformer connection, and apparently we'll talk on the current phase introduction to delta Y transformer connection, part 3. The part of presentation between line-to-line voltage and phase voltage in part 3 will cover the relationship between the line current, phase current, and delta Y transformer connection. Let's pick up the relief of our secondary side of the transformer, where our transformer is connected in a way with is neutral grounded. We understand the line current or line-to-line current, as I like call it, petroconductor. Since we have assumed that the secondary is our load side, we understand that the line current we followed through our line to our load. So line-to-line current is flow through line. A line-to-line current B will flow through line B, and line-to-line current C will flow through line, and D will be filled. Or we decide to call our line current OK to our transformer is connected in delta on the primary side of the source. So this is where our source current well came from, the line to line. Similar to line A, flow to line B. The line C is flow to current line C, respectively. Remember, this is line-to-line current that comes from the source, the generator, utility, or the grid. Let's now talk about phase currents. We understand that the phase currents flow transformer windings. So let's start on the secondary side. The transformer is connected in Y. We should expect phase up current to come from winding A and flow to our load, and similar speed current come from our winding B and flow to our load, and also phase the current come from winding C and flows to our load. For a Y connected transformer, we should expect a base A current and line current to be the same. Since base current flow in transformer windings, the delta transformer connection is no exception. Let's begin with winding. Since we know that the secondary phase a current flow are of that on the secondary side, that simply means that the primary phase is current flow in the dot of the primary. So primary phase current will flow into the dot, and the secondary phase BSEE current will flow out of the dot. This makes sense, right? We're simply following the dot convention. If the current goes into the dot from one side, current must blow out of the dot on the other side. Similarly, current must flow into the dot on the primary side. To make a secondary phase current flow out of the dot on the secondary side, and lastly, phase current must flow into the dot of the primary side, and the secondary phase current flow out of the dot on the secondary side. Introduction to the delta Y connector transformer, part 4. In this part, we are now going to use square flows and node to describe the relationship between line-to-line current and phase current. Let's start from node E1. We can visually verify that the line current flows into node E1. Base current C also flows into node E1. However, base currents flows out of node E1. So when we apply KCL or Kirchhoff's current law, we can simply express as line current applies base current C equal base current A, or in other words, line current A and base current C goes into node E1, which is why it's on the left side of the equal sign. However, since phase current flows out of node E1. It's on the right side of the equal sign. Simple right. The currents that are flowing into node E1 is equal to current that are flowing out of node E1, or simple line current. A plus phase current is equal to phase current. Similarly for a node B1, line current B plus phase current A is equal to base current B. Line currents B is current are flowing into node B1, but base current B is flowing out of node B1. And for node C1, line currents base current B is equal to base, and for node C1, current C plus base current is equal to base current line. Line current C and base currents B are flowing into node C1, but base current C is flowing out of node D1. Introduction to the delta Y conformer connection, part 5. So mao na atong illustrate sa part for nodal analysis on node E1, not B1 and node C1. At the relationship between line current and B phase current, and these are the equation that we come up with. Line current A is the base current equal base current to, right now we're going to evaluate this particular equation and look from a Fisher diagram perspective. So this equation into something that makes a little more sense. Okay, let's all we're going to do is to make the space current also. So ato na i-write ang equation. So solve for the line current. So line current is equal to phase current minus phase current C. Similar, line current B equals base current B minus phase current A, and line current C equal to base current C minus phase current B. Okay, so now written equation like this. Let's define our base value. So our base value of the current that are flowing through our windings. So we're going to define what are our things occurring into is going to look like we're going to define base B current and base C currents. We're going to define this current and create a balanced system. So let's say that base current on primary side equal 1000 and 0 degrees equal 8000 ohms at 240 degrees, and lastly page current C equal 1000 ohms at 120 degrees. So muna natin drawing on Fisher, and as Fisher just the current that are flowing through primary windings. Mind the big picture of what we're trying to solve. We're performing the Fisher analysis because we want to relate this line current. Actually, this phase current and this phase current, so we're doing a nodal analysis on node E1. Actually, trying to solve with our Fisher diagram is this particular equation. Right, we're going to try to find out what this line current equals when we subtract our phase current minus phase current C. Let's draw as picture diagram. Alright, so this is the what our picture diagram look like. Next line right here at the 0 degrees line is our reference line. Okay, and this Fisher are going through our reference line at 0 degrees. This is the phase A current, and what we're seeing is from this origin point here to point here, is 1000 ohms, and the angle is a 0 degree, which is the same direction as a reference line. This picture is our PSB current from this region to this marker is 1000 ohms, and this angle, which is 214 degrees, of what we need to find the angle of this from this reference line going in a counterclockwise direction until we've gone to 40 degrees. So this angle is 240 degrees. We are defining the space B current at the angle of 240 degrees, and lastly this picture where our piece cranks again from origin to the end of the tip is 1000 ohms, and the angle from the reference line going counterclockwise PC current, which is the current door, equal 1000 amps at 120 degrees. So let's mark this angle here. So we're saying that this angle here is 120 degrees, and we're saying that this angle is here is 240 degrees. So we're going to take these pictures and subtract phase current with phase current introduction to delta Y transformer mechanics part 6. So kanina part we talk the voltage spacer diagram for the delta transformer connection. So in this part, if I measure the voltage across line A, this ground point, I'm going to call this voltage BEG. So drawing another arrow for indicate BG, that's going to be measured across line B and ground. So auto arrow para ma-illustrate. Then lastly, BCG is the voltage across line C and ground. To understand the spacer for the line delta connection is really rooted in that understanding VEG versus BAB. So BAB is the voltage across line and the line B, which is essentially equal to PC voltage. So we're talking about the difference of understanding phase voltage versus BEG voltage. And oftentimes this BEG quantity is also called VIN. And this also.
And oftentimes this VA to G quantity is also called VAN and is also referred to as this reference quantity. Okay, this reference quantity.